Alrighty, folks. So we're getting deep into two-dimensional motion. We've already talked about projectile motion and circular motion. Now let's take a little detour and talk about g-forces. Now, g-forces are something you likely have heard about. You know, somebody going in a jet plane experiences 5 Gs, or someone going on a rocket to the moon feels several G's of force whenever they, blast off. But I actually don't like the phrasing of G-forces. In fact, G-forces is a bit of a misnomer, in my opinion, because what is G? Well, this is referring to little g, our acceleration of gravity. And that's an acceleration, not a force. We now know the difference between these two things. They are closely related. We know from Newton's second law that forces cause accelerations. But nonetheless, a g-force is not really a force, it is an acceleration. So let's look at how we compute it. We really are just coming up with the number of g's of acceleration. It's the force required to cause some multiple of g of acceleration. Remember, g is 9.8 meters per second squared. So if you're accelerating at, say, 19.6 meters per second squared, 19.6 meters per second squared is 2 times g, or 2 g's. So all you do to figure out how many g's is take some acceleration, and you divide by 9.8 meters per second squared. That number you get is how many g's of acceleration. Now, you might have noticed that I left off the minus sign here. We're not really worried about direction in this situation. This g-force would be more like a scalar quantity, just a magnitude, no direction here. So don't worry about the minus signs. I don't really care about direction. I just care about how extreme the situation is. That's why I'm referring to it in numbers of g's. And if you took an acceleration divided by 9.8 meters per second squared, that then gives you how many g's. If you wanted to compute the force, the actual g force that we started talking about, you would just use Newton's second law, F equals ma. Only you now know how many g's you have. Remember, that's an acceleration. So you would just plug in, 2g, 3g, 4g's, 5g's. And it doesn't have to be an integer number, a whole number. You could have 2.5 g's, or however many you needed to. But you would just take that value and plug it in for your acceleration, and that would tell you how much forces is necessary. And we'll probably look at an example in class about, how rapidly you might need to spin somebody around in a circle, one of those centrifuges that they train astronauts in. We're going to look at how fast it would have to spin to simulate a shuttle launch. This is something they really do to astronauts. But that is my brief synopsis of g-forces. Mainly, I want you to remember g is an acceleration. It's not really a force, but it is tied into force. So you can take a number of g's, multiply it by your mass, and that tells you how much force it would take to give you that many g's of acceleration. All right, the last topic I want to cover before we close out this chapter is rotary motion. Now, we already talked about circular motion, and circular motion is very closely related to rotary motion. Rotary motion is really like a lot of circular motion at once. The best example I like to point to is imagine a spinning record, like a record player. Not too long ago, I would expect many of you wouldn't even know what this is, but vinyl has sort of made a comeback. So as you watch the record spin, you might notice that if you put something on the edge, it moves pretty fast around the edge. The closer you put it to the center, it seems like it's moving a little bit slower. And if you move all the way to the exact center of that record, well, then it doesn't really move at all. It just sort of spins in a circle. Well, what you're looking at is the fact that different points or different radii move at different speeds. And that's because they're tracing out different size circles. Some circles are bigger, some are smaller. The closer to the center, a smaller circle. Further out, a bigger circle. And if you drew a line straight across your record, that whole line would make a full revolution at the same time. That is, any point on the outside has to go around this big circle in the same amount of time that a point on the inside goes around that small circle. Well, clearly this is covering more distance in the same amount of time, so these points on the outside move faster than the points on the inside, with the extreme case being right at the center. They don't really move at all. You've dropped down to a radius of 0, and you're really just spinning. You're looking in different directions, but not really changing your position. So, we have different speeds everywhere, but there is one constant rate of change, and that is the rate at which the angle is swept out. This angle is the same for a point on the outside versus a point on the inside. And so rotary motion is also sometimes referred to as angular motion, because we're focusing on how the angle changes rather than how any specific position changes. And because of this, instead of using meters per second to define how something is moving, how its position is changing, we can define angular motion or angular velocity with radians per second. How much does your angle change per second? And you might not have used radians per second, but I'm sure you've actually probably looked at something or heard of something that is measured like this. For instance, what about RPM? That is revolutions per minute. A revolution is similar to a radian. It's 2 pi radians. It's a full circle. That's saying how many full circles do you make every minute. It's the same idea, measuring angle per time and using angular velocity rather than saying this thing is spinning at such and such meters per second. Well, some pieces of it, like the outside, are moving faster than the inside. So we can't really use one value of velocity to describe how that thing is moving. We instead use angular definitions. Well, just like we have acceleration and velocity, we have an angular acceleration that describes how angular velocity changes. And just like velocity would be measured in meters per second, and acceleration is then meters per second, or meters per second squared, angular acceleration is radians per second squared. How your radians per second are changing per second. Radians per second squared. And of course, I sort of skipped this one, but if we go back to how do you describe position, where are you? You use angle. We don't necessarily use any specific measurement. We don't use a length measurement to describe position. We describe what the angle is, and we would use radians as our SI unit, but you could also use degrees if you wanted to. But you measure position as angle, and then how your position or angle changes is velocity, angular velocity, radians per second, and how that angular velocity changes is angular acceleration. So we're not going to do many problems or problem solving with rotary motion, but I wanted to make you guys familiar with it and the ways in which it's similar to circular motion, but different. Essentially, any one point goes in a circle. If I just set an object on a disk, it's going to trace out a circle. But the entire motion of the motion of the entire disk is better described using rotary motion or angular motion. So that's it for Chapter 4. We now have seen a few examples of motion in 2 dimensions, and we also got a deeper understanding of vectors and how vectors are really very useful whenever you move into higher dimensions. We'll be working lots of examples of these. I hope to eventually record some videos of example problems from projectile motion and circular motion. But for now, I think I'll save those for our class time. So hope you guys enjoyed. I will see you next time for Chapter 5 when we get to work, energy, and power.